Mm-hmm. But I thought we agreed on assignments, sir.
Assignment. Oh, you agree on assignment, but look at the time now. The time frame for the exam is fast approaching. If you have to begin assignment, I don't know where you have time to work on the assignment. But let's see if you can work on the assignment within 1 week. Is that possible?
If the
But
assignment is not much, it could be
I
possible.
already had an assignment for 504 already.
So, Imole,
Yes, sir.
we agreed on that, right? We agreed on the test or the assignment. Can you
So
work
I
with the
think last
assignment
statement
within
prof
1 week?
was speaking.
I can't hear you.
So I think like it depends on like because what prof suggested was that we're going to probably take a picture and all those property stuff. So it depends on what the requirement of the assignment are. If you're supposed to write a lot of words, then maybe I don't know. But if it's something that is not too lengthy and something that is quite practical, I think we can do it within 1 week, sir.
No problem then.
And sir, we have lab for 504 already now. You gave us then when we were in school. Do you want to capture in
504
that?
is this 528, brother. This
Okay,
528.
okay, okay, sir. Right.
Don't worry about 504. We are about 528. And if there will be a test for 504, we will let you know about that as well. So, in a few minutes' time, Prof will join us. Kindly be patient. I expect him to join us by now. Please, once again, be patient with us. He will join us in a few minutes' time. It's just for him to log on to his internet. While we still wait for him, is there questions, comments, remark as regard last class? Imoy, do you have any question?
So I think the only thing I have to ask about is like the material props we are going to get for 528, the corrected material. So I don't know, like how soon are we going to get that answer? And then you also mentioned last week that you're going to drop our scores for
Yes, for the material,
comparisons.
you will get it today.
Yes, sir.
Once immediately after the class, you will all get the material.
Okay. All right, sir. Thank you, sir.
So just be patient with us. Thank you. Prof will join us soon. Just be patient. So please, patient, Prof. join us right now. Imole, inform your course mate. I'm not can't see this is we are just
Yes, sir.
where are others?
And some are like on the way.
I didn't get that.
And some are waiting for Prof to join us, sir.
Prof will join us soon. I just told you now.
Yes, sir. Yes, I informed them, sir. So there should be time soon.
Good afternoon, everyone.
Good afternoon, sir.
This is 528 class.
Yes, sir.
Okay. I can see that only 9 people online. What are the others?
Sir, they're coming.
Hello?
They're on their way.
The class governor,
So,
you are online.
the
Class
Lord
governor is online.
Sir? Yes, sir. I'm here, sir.
Yeah.
Yes, sir.
You're
Yes, sir.
welcome.
Thank you, sir.
Now, I want to share my screen,
Okay, sir.
assuming that others are joining. Can you see my screen? Is somebody see my screen? Hello?
Yes, sir. We can see your screen. Yes, sir.
Okay.
Not yet, sir.
I cannot see my
It's
screen.
about to start this.
I can see your screen, sir. Example of vector manipulation, sir.
Okay. You're right. Class governor, you're not seeing it, Abby? Hello, class governor.
I think he's having network issues, sir.
Yes, sir. We can see your screen. We can see it. You can see it, sir.
Okay. Let me make it bigger. Can you see my screen now? Can you see my screen now?
Yes, sir.
Can you see my screen?
We can,
Yes,
sir.
sir. Yes, sir.
Okay. You are welcome to this class 5QA, another in the series. The last time we met, last week precisely, I promised I was going to be able to give you a smaller note, but in an attempt to make it smart, the note got bigger. I have 440 something pages instead of having something less than 70. So the challenge we have now is to reduce and cut off the necessary parts, and then you have the complete lecture note. Now, but for today, we just go through some selected pages from what we have, and then you get the corrected notes later today. Now, last week we discussed the issue of forming an equation for a ray. And we discussed some vector properties in the process. So we'll just review some of those vector properties and vector calculations, which you can expect in the exam. We are going to just start with that. Now let me locate the page. Now, you remember that we said any point in a three-dimensional coordinate system, whether virtual or real, can be represented in Cartesian form as a point P having coordinates X, Y, and Z. That's in the Cartesian coordinate system. It's represented as a column vector X, Y, Z, where the X, Y, and Z are the coordinates of a point. And before this time, we discussed different types of vectors where you have free vectors and position vectors. We have discussed all of that, or you get it in your final lecture note. And now, before we start, we have a date for our exams.
Yes, sir. I think it's in 2nd of September.
Okay, so we'll have the opportunity of having a few more lectures. We should be rounding off now.
Sir.
And now you will see this page where I have types of vectors in 3 space. Dimensional coordinate system. Now,
yes, sir.
On the left, you see different types of systems, different types of vectors represented as lines on this page. And any vector that originates from the origin of the coordinate system is called a position vector. We have said that before several times. It's called a position vector. And any vector that does not get to the origin is called a free vector or a line segment. Now, as you can see this label here, this line that goes from the top of this vector to the top of this vector is called a free vector or a line segment. This vector that is moving away along its own line is called a free vector. This is also a free vector. But any vector that originates from the origin is called a position vector. And that's what we use to represent when we write the coordinates of a point in surveying. It means position vector. In surveying, X, Y, Z are the coordinates of a point, and they are form a position vector. So if a position vector is different from a line vector or a free vector. A position vector is a vector that ties a point to the origin, whereas a free vector connects 2 points. Connects 2 points, but not in the origin. So it is called a line segment or a free vector. Now, recollect that when we did the geometry of the photograph, what we have there are just lines. So some of them are position vectors, some of them will be free vectors. But what is important is to be able to determine the property of a vector. And one of the properties is the magnitude. Another property is the direction. Because we will need that when we are doing our calculation. So we will need to, this is another view of a position vector. Vector O is a position vector. Vector P is a position vector. Or P prime is P minus O, and that is P prime. That's a line segment or a free vector. Now, I will show you a vector that is not tied to the origin is a free vector. It is invariant under translation. In other words, when you change the vector by adding another vector to it that is along the same line, does not change the free vector. It often results as a difference between two position vectors. That's the difference between them. And the traverse line in the survey is a free vector. Now that's why you add delta x, delta y to the previous one to be able to get, this is because they are free vectors. But once you add them, then get position. Now, a vector whose magnitude is 1 is called a direction vector. A vector whose magnitude is 1 is a direction vector, and it can be a position vector or a free vector. So every vector has a direction property, which is represented as LMN. The position vector itself is X, Y, Z. But when it turns into a direction vector, it has magnitude 1, and it is labeled as a color matrix LMN. Now, where LMN are numbers computed as direction ratios of the components of the vector in the X, Y, Z axis. Now, this can be expressed as L is X over magnitude of the vector P, and M is Y over magnitude, N is Z over magnitude. So this LMN will be a direction vector, and when you find its magnitude will be 1. So that's another property of the vector, that the vector has a direction, and that direction has a magnitude of 1. Now, P is the magnitude in double bar, represented in double bar means magnitude of P is the magnitude computed from this expression, which is the application of Pythagoras theorem. Then another property of direction vector or a unit vector is that the sum of the squares of all the direction elements is equal to 1. Okay, the square of the elements is equal to 1. So when you calculate the direction of the vector and then you sum the squares of the numbers, you should get the number that is 1. Unit vectors are also called direction vectors because the relationship between their components and the cosines of the angles, you can find the angle between two vectors, two position vectors or two free vectors by using their direction vectors. We are going to work an example of that later on. Now, a vector, which is a position vector, or can be a free vector also, is X, Y, Z, where these are the elements of the vector. If it is a position vector, X, Y, Z will be the coordinates of the point. But if it's a free vector, the X, Y, Z will be delta X, delta Y, delta Z, because it's a line segment, then it's a difference between 2 points. So delta X is X1 minus X2, delta Y is Y1 minus Y2, delta Z is Z1 minus Z2. So if it is a line segment, X, Y, Z will represent the differences in coordinates. But if it is a position vector, this X and Y will represent the coordinates of points. Okay, so you should know the difference between a line segment and a position vector. The line segment does not pass through the origin. The position vector is a coordinate which is based on the origin of the coordinate system. Now, the magnitude of a vector, whether of a free vector or position vector, can be computed by the squares of, I'm using the Pythagorean theorem given here. Now, this is just to refresh your memory. We have discussed all this before. Now, I'll move on. Now, the direction of a vector, which we represented as LMN, can be computed also in terms of cosine of the angles that the vector makes with the coordinate axis. You have cos x for a two-dimensional vector, that is a vector on a plane. It has L and M, where L is cos theta x. Theta x is the angle that the vector makes with the x direction, x axis, and it's computed as x divided by magnitude. So you already know how to compute that. Now, well, that is for a three-dimensional coordinate system. LMN are computed at the angle that the vector makes with the coordinate axis. For example, theta x is the angle made by vector p with respect to the x-axis, and theta y is the one made by the complement. That is the p, the angle that it makes with the y-axis. For a three-dimension, it will be theta x, theta y, and theta z, where theta z will be the angle made by the vector with respect of the coordinate axis. Now, you recollect that we gave three representations of a vector, of a position vector, of any segment vector, as in a three-dimensional, we can give it in a local spherical coordinate system where we have horizontal angle and the altitude. Measure horizontal angle and the altitude, or zenith angle. Zenith angle is the complement of the altitude. I hope people are familiar with all those terms now in 500 level. Now, we can express the LMN, that's the direction, in terms of the horizon angle and the vertical angle, or the altitude that you measure. For example, when you are doing your solar observation, you always measure the sun in the local horizon system. When you go to do your astronomy and you are doing solar observation, what you are assuming is a local horizontal coordinate system where you level your instrument and you measure some horizontal angles and also measure the altitude of the sun. You measure the horizontal angle from a known line, and then you measure the altitude. You can also get your horizontal angle as a difference of longitude of the place, which is related to time. Okay, so you can compute your H and V. V is the altitude that you measure of the sun, and then you carry out your calculation. So it's the same thing in a local coordinate system. You can express any vector. Any vector, for example, the vector will be a point, a line that connects your position to the sun that you are observing. Okay, so it has horizontal angle and vertical angle, which you use to determine your azimuth or whatever you want to do. Now, well, this coordinate system that you have is a standard coordinate system in a right-handed system where the IJK are just used as vector to indicate vectors, the operation in a number. You write the position of the point or the coordinates of a point. Instead of writing it in column X, Y, Z, you can write it in algebraic form. And the algebraic form will allow you to add all the elements x, y, z. So you say xi plus yj plus zk is the same as the column xyz. Okay? But written in algebraic form, as we shall see in some examples that we have. I just now we have a vector that is written as xyz. This vector xyz can be written in algebraic form as x multiplied by the vector I, as the expression for vector I, plus y multiplied by vector j plus z. This one is z, that's an error. Z multiplied by vector k. And you can see that this position vector or the segment vector is xyz and is written in algebraic form as xi plus yj plus zk. Okay, this one is just to explain to you how that is done, because if you multiply x by this vector, you get x. Multiply y by this vector, you get y. Multiply this one by this one, you get z. So you have the vector x, y, z can be written in algebraic form as this. So you can be given a vector and be told that this is the position vector of a point P or point A or whatever. So you can be given the vector in this form or in the column vector form. And of course, remember that you can express the vector also in terms of horizon and horizon coordinate system, or in terms of the direction angle coordinate system. Okay, for which we have given a lot of repetition in the material. That's why the page is also zoomed up. Okay. Now, we don't have to worry so much about this. The magnitude of a direction vector is always 1, as you can see from here. Then the dot product, which of course we have to explain to you. The dot product is used to multiply two vectors to get the angle between them. We use the dot product to get the angle between them, and also use dot product to multiply two position vectors or two direction vectors to get some result, as we can see later if there is time. But just memorize this one, that the dot product of 2i direction, 2j direction, and 2k direction will be 1. And the magnitude of each of them will be 1 also. Now the dot product of opposing element, I dot j, j dot I, and k dot any of these will be 0. Okay, and those are just for your information. You don't have, ignore the cross product for now. Cross products are used to find areas of triangles and polygons and so on. But we are not dealing with that now, this course. So we can ignore this page, although it will be removed in what you are going to get finally. Now, we have a vector that can be written in terms of magnitude and direction. The magnitude is put P inside 2 bars, multiplied by the direction vector, Li plus Mg plus Nk. That's a direction vector. You can write a vector in the XYZ form or in the algebraic form, and also write it in the the unit vector form, where you have P magnitude plus direction, magnitude and direction form. These are just different ways of representing position vector for you to be able to get used to how position coordinates are manipulated in calculations and also practical work. Now, so obviously there's a matrix error here, but this is showing a column arrangement of the direction vector. This is also a column arrangement of the horizon vector, direction vector in our horizon system. This is the column for representation of a vector in the direction vector, the direction angle coordinate system. Now, if you write a vector in algebraic form and also in horizon system, then you're going to have the magnitude as P represented outside, cos V cos HI, cos V sine HJ, and sine VK. So this vector is the same as the XYZ vector, but now expressed in direction and magnitude form, in algebraic form also. That's the algebraic expression. That should be highlighted in red as we go along. Note here that we are in a VH coordinate system. VH coordinate system or RVH coordinate system. R is the magnitude, which here is represented as P. RVH coordinate system, where G and H are vertical and horizontal angles, respectively. Note that they are observable using the theoretic horizon and vertical circles. To measure them, the advantage of this method of representing coordinates is that it can be measured using a theodolite, measure the horizontal and vertical angles with horizontal circles and vertical circles. Now, we said the last form of point representation are particularly useful in analytical mechanics and time series modeling. They are also useful in photogrammetric work. The relationship between the horizon system and the direction cosine form is very important in many applications, including astronomical studies and terrestrial image metrology. It is helpful to collect all our vector representation together for easy reference. It's shown below. Now we have a vector in a standard Cartesian coordinate system, XYZ, represented as a column vector. I'll tell you what that is. And this column vector can be represented in another way, algebraic form, by using the IJK method. And that's what is written here, algebraic form. So if you are given a XYZ and you are asked to convert it into algebraic form, all you just do is to add XI plus YJ plus ZK. Okay? Now, if you are asked to represent it in magnitude and direction form and algebraic form at the same time, then you are going to find the magnitude. You are going to now divide every X, Y, Z by the magnitude, and then write it as magnitude and direction. For this vector, P in 2 bars is the magnitude, and the bracket X over P, Y over P, Z over P in algebraic form will now form the direction. So we'll be able to identify P as the magnitude and the direction as X over P, Y over P, Z over P. And this can be abbreviated as magnitude times Li plus Mg and Nk, where L is X over P, M is Y over P, N is Z over P. Now you get this together in your lecture. Now, the same vector, if represented in direction cosine form or direction angle form, is going to be P equal P magnitude and multiplied by cos theta xi, cos theta yj, cos theta z, where the cos theta x, cos theta y, cos theta z are the cosine of the angles that the vector makes x, y, z axis. And of course, in the horizon system, P is written as magnitude plus cos V cos HI cos V sine HJ sine VK in the right-handed coordinate system. And what you have, magnitude is computed as using Pythagoras theorem. So if you are given a vector or a position vector in terms of x, y, z, and you are asked to express it as algebraic form in the horizon system, we use one in the middle here. You are asked to express it in the direction angle coordinate system. You use the first one. The horizontal system, you use the second one. And then the third one is the x, the not flat flat XYZ P will become XI plus YJ plus ZK. Okay. We shall see some examples. Now, there is a problem here, which is stated as an example. He said a photographic point on an image of a focal length 100 mm has coordinates x minus 45, y is 48 mm. If we represent these points in a virtual 3D coordinate system, to become minus 45, 48, and 100. That is equivalent of x equal minus 45, y equal 48, z equal 100. So find the horizontal and vertical angles it makes in a virtual spherical image coordinate system. What we are asked to find here, we are given the x, y, z form, and then we are asked to find horizon system, that is the V and H angle, the horizontal and the vertical angles that it makes the virtual spherical image coordinate system. In the last second part of the question says, express this point in algebraic form in terms of those spherical coordinates that we are getting. This solution has been provided here. Now, using the coordinate conversion formula which we have given before, the rectangular spherical rectangular to spherical can be directly computed from the vector. This is the given vector, minus 45, 48, and 100 mm. Now, in magnitude form, we compute the magnitude using Pythagorean theorem, 45 squared, 48 squared, 100 squared. That gives you 119.78. That is the magnitude of that image vector, which is given as XYZ here. Now, the vector in magnitude direction form becomes P equal the magnitude which we have computed, then X over that magnitude, I, that's in algebraic form, Y over that magnitude, G, and Z over that magnitude. So by just substituting this magnitude and this value of X, I've gotten the algebraic expression for that vector in the XYZ form. Now, in the altitude horizon system, it will be written from the formula that we have before, the same magnitude, but now cos V cos H, cos V sine H, and sine V will be the direction of that vector. And of course, this can be completely converted using the formula we have. H is 48, which is y over x, which is negative, and you get that angle as 180 degrees minus 46, which is 133 degrees. That's what H is. Okay. Now, V, the vertical angle, is arc sine, and you can see that from here, this expression is known. This expression is known, and it will be equivalent to this expression, cos V cos H. And the y over p will be equivalent to cos V sine H. So by equating this and this to this and this, you can get those the H coordinate. Now, sine, this one is easier. Sine V, you can get your vertical angle by finding the arc sine of this one. And that's what they are doing here. Although the formulas have been given before in your note, which will be repeated. Now you can compute H from this equation, and then you can compute V by finding the arc sine of 100 over P, and then you get this angle. So in algebraic form, the position vector is the same as 119, that is the magnitude, cos 56, cos 133.15, then cos 56, sine 133, then sine 56. That's what it is. Solution form. So now this is saying alternatively, you can reduce the original vector to magnitude and direction form, from which we can compute the virtual spherical angles as follows. Given the vector, which is the same, it can be put in the magnitude and direction form as P equal this, where P is given as before. Hence, P can be expressed as this. So each of these is allocated to, this is assigned to the vector, this vector. So you can find the arc cosine, the arc cosine of the expression, and you get the expression for theta x, theta y, theta z. Now, we have seen this one before. You can do the other one as an assignment, be able to convert to, to determine theta x, theta y. That's by equating all these to the coefficient that will compute from the coefficient that will compute from dividing each one, by x, dividing x by magnitude, dividing y by magnitude, and dividing z by magnitude. You can equate it to any of these and then solve the problem. But the formulas have been given before. I hope to be repeated as we go along. Now, make sure that you can solve that problem because it can come in your exam. Now, we have obtained the horizontal angle, horizon angle, and also the direction angle. Now, this is an exercise which you should do and submit to the class governor as your assignment number 1. Express the following position vectors in terms of magnitude and direction cosines. Coordinate 3, 4, 5, coordinate 5, 9, 12, and coordinate 4, 9, 16. So complete that and find the magnitude and direction. Express those vectors in algebraic spherical form and algebraic direction cosine form. So you'll be able to do that as an assignment and submit to the class assistant lecturer. Now, this is also important. Given two space vectors, 3D vectors, two direction vectors are given as L1, M1, N1, and L2, M2, N2. The angle between them is given as cos theta equal L1, L2 plus M1, M2 plus N1, L2. So if you are given the direction vectors and you want to find the angle between them, then the cosine of the theta of the angle between them is equal to the direct product of L1 times L2, M1 times M2, N1 times M2. When you sum them, then you can find the angle as arc cosine of the sum of all of these. Okay? Where L1, M1, N1, and L2, M2, N2 are the direction cosines of the two vectors. Hoping you are still seeing my page. Okay? In general, the unit vectors or direction vectors obey the following rules. For any direction vector, the sum of the squares of the elements will be 1. In other words, vector has magnitude 1. Because if you find the magnitude using Pythagorean theorem, it's L squared plus M squared plus N squared, 5 square root, which is 1. Square root of 1 is 1. Now, for perpendicular vectors, if those two vectors are perpendicular, then the angle between them, the cosine of the angle between them is 0. That means that the angle is 90. Cosine of 90 is 0. Cosine of 90 is 0. So when the cosine of the angle between two vectors is 0, then the two lines are perpendicular. They are perpendicular. That means the angle between them is 90 degrees. And when the angle between two lines is 90, the vectors are said to be perpendicular vectors. For parallel vectors, the angle between them is 0, and the cosine of 0 is equal to 1. Sine of 0 is 1. The angle between two vectors, therefore, can be computed as cos theta equal L1, L2, M1, L2 plus N2, N1, N2. Now find the angle between these two vectors, I, J, K, and I plus J minus K. These are two vectors. And you find the angle between them. By applying that formula, then you can get... now, since these are not unit vectors, even though each is a combination of standard unit vectors along the axis, you cannot use the direction cosine formula directly. Instead, work with the inner product expression. Because we have another expression for computing the angle between two vectors. Okay, but at the same time, you have to multiply the element. In this vector, this is a vector ijk. The coordinate equivalent of ijk is what? Who knows what the coordinate equivalent of that vector is? I'm talking to the class.
XYZ, sir.
And what is the value? Value of x, the value of y, the value of z in that vector I plus j plus k. To save our time, x is 1, y is 1, z is 1. That's the vector ijk. You agree?
Yes, sir.
What is the value of the coordinate of the other one?
Okay, x is 1, 1, y is 1, z is minus 1.
Minus 1. Minus 1.
Beautiful. So those are coordinates, and then that's the algebraic form of x is 1, y is 1, k is 1. And the other vector is x is 1, y is 1, k is minus 1. Okay, so by applying it to our formula, we can get the angle between them, between those two vectors. Now, we are not to study the triangular law now, even though you need them. It just shows you how to can add two vectors. You add two vectors by adding their components. That's not, let's go ahead. Don't have time. We can subtract vectors, we can add vectors, we can multiply a vector by a number, in other words, make it smaller or bigger than its former size. And those are things that are being treated here. You can read them up on your own. By multiplying a vector, the element by a standard S, you are scaling up or scaling down the magnitude of the vector. It does not affect the direction. In other words, when you have a vector expressing magnitude and direction for, multiply it by a number, you are affecting only the magnitude, but the direction remains the same. Okay, that's the message in that place. You can multiply a matrix and a vector by a matrix. They are compatible, but we will not get to that level this course, so you can read them for interest's sake. Now, we have other examples that are given, which you are going to have to use. A vector that is in a plane will have only two elements, because the plane is a two-dimensional object. Now we can move ahead. That's not very important. And this also is not very important. Those are examples of what we have done before. Now, the inner product or scalar product of two vectors is important. Important in the sense that we are going to use it to derive horizontal and vertical angles from vectors in our photogrammetry. So we need to get used to this expression A dot B, which is given as the magnitude of A by the magnitude of B times a cosine of the angle between them. So if we know A dot B, right, we can compute the magnitude A, magnitude B, and then the cosine of the angle theta can be obtained. So the cosine cos theta is going to be A dot B over the product of the magnitude of the two vectors. Okay? You don't have to worry about the algebraic expression there. Unless you are a mathematically inclined person, then you can. That's the expression for the algebraic expression for this same inner product, which is going to give you a single number. And that's the result that you're going to have. It's going to be AX times BX plus AY times BY plus AZ times BZ. That's the inner product. So when you're given two vectors and you have to find the angle between them, then of course find A dot B first. Once you find A dot B, which is just the product of the corresponding vectors, then it is the length of each one. You have find the length of this one, find the length of this one, then the cosine of the angle, just divide this one by that one, you get the correct angle. That's what is given here. It should be highlighted. Final thing that you get. We have an example. So given these two vectors, find the dot product of these two vectors. So multiply their corresponding elements, sum them together. That's the linear product or scalar product. You don't need cross product for now. You will need it when you come for your masters. Now, scalar triple products will be needed later, not now. The scalar triple product compute volumes. The cross product will compute areas. The scalar triple product will compute volumes. And then volumes can be interpreted in different ways in engineering work and in calculations of different quantities in surveying and mapping. Now, parametric equation of a straight line. And for me to go ahead, well, I'm giving the formula here, even though it's not highlighted. Now we have this equation of a line that runs between 2 points. And we are going to make an assumption. There should be a drawing close by here. So, let me skip this. See, a lot of repetition in this material. Now, this is what I'm assuming that you are still seeing my page and you are hearing my voice. This is a drawing that shows an origin O. And then there are two vectors that take off from the origin, P0 and P subscript A. Now, these P0 and P subscript A are position vectors. And the line that connects their ends, their two tops, is a line segment or a free vector, as our previous definition. A free vector or a segment vector runs between 2 points. It runs between 2 points. It is also a vector, but it is a free vector. A position vector is tied to the origin and it is coordinate. A line segment between 2 points is not coordinate, but it is what? It is coordinate differences. I say it again. A position vector is a coordinate, but a line segment or a line is a vector of coordinate differences. Do you agree?
Yes, sir.
Yeah. So you know the difference between a free vector and a position vector. The position vector is a coordinate. The free vector or a line segment is coordinate differences. So when you are given a line, X, Y, Z, and values are given. If it is a line that is a free line or free or line segment, it actually indicates coordinate differences because a line is the difference between 2 points. So PA minus P0 will be the line segment, for PA and P naught are coordinates. Okay, so we now form the equation for the line segment. We form the coordinate for the line segment. That same coordinate and that same line equation will apply to even the P naught and PA that are position vector, only that the beginning of the line is start from 0. Okay, so that's what we are going to find. We want to find the equation for this line because in our geometric analysis of the geometry of the single photograph, we find that from the camera, the point, a ray is going, from the object, a ray is going through the lens camera, the camera lens, and to form an image point. So in that case, we can regard it as a line segment and then form an equation for it to use to do further calculation. Now, this equation is given the same form that we had before. P equal P naught plus a small proportion. Yes, who is there? Who is not? I'm in a lecture. Who's there? Okay. Now, the interpretation of this is that any point P on the line segment is given by the starting point of that line plus a small percentage of the length of that line. Small percentage of the line segment. P naught minus PA is the line segment. And then we now add a small percentage of that line to the starting point, then we get any point P. That's the interpretation of that line, of that equation. Okay, any point P on the line, let's go back to that line. Any point P on that line, say at this point, is going to be the point P naught, which is the starting point, plus a small segment. Maybe I should have added one line here, another position vector here, and put it as P. P would also be a position vector, okay? And it can be computed as P naught plus a small segment T. That will give you any point on that line. That's what that equation is saying. So, and the equation is given as P, any point P along that line segment is the starting point of that segment plus the small proportion of PA minus P naught. PA minus P naught is the entire line segment. The small proportion, if this T is 0, then the point P is at P naught. If T is 1, if T is 1 in that equation, what will be the final expression? P will be equal to what? I'm talking to the class.
Hello, sir. When T is 0, P is equal to P naught.
When?
You said when T is 0, sir.
When?
You said when T is 0, P will be P naught.
P is what?
P naught.
P is what?
Okay, no. Oh, when T is 0, P is P naught.
P is P naught.
Yes, sir.
What about when T is
Yes,
1?
sir.
When T is 1, you just have P as.
When T is 1, P will be equal to PPA.
Beautiful.
Sorry, P will be equal to PA.
That's all.
PA, yeah.
That's all, because when T is 1, you have PA minus P naught plus P naught. You cancel out and P is at point PA. That's why we say this equation, the last line here is saying that T is between 0 and 1. Okay, T is between 0 and 1. When T is 0, P is at P naught. When T is 1, P is at PA. And look at that drawing again. When T is 1, that equation tells you P is at point 0. When T is 1, is at point PA. So that equation applies to any point along this line by varying the value of T. And that's why we call it parametric equation of line. The line equation you are seeing now is different from the ones you have learned in other courses. In photogrammetry, we use parametric equation to simplify our calculations, knowing that we deal mainly with vectors, and these vectors are very useful in parametric form. Even in geodesy, we use parametric form to handle complicated equations and calculations. Okay, so this parametric equation of a line that runs from point A to B, parametric form for any point on that line segment is given as A plus T times B minus A. So that would be the equation of the line, where T takes value from 0 to 1. T takes value from 0 to 1. So that is the equation. In this case, we have used P naught and PA as the terminal of the lines. So any point P in between those 2 points is written as the starting point plus a small fraction of PA minus P naught. Now, if T is half, what will happen?
It will be midway between P naught and PA.
So it will be midway between P naught and PA. If T is 1/3, then it will be 1/3 of the line, right?
Yes, sir.
T is 5/8, then it's going to be fifth point along the line, and so on and so forth. So that parameter T is undetermined, but it takes value from 0 to 1. Now you see how we use this equation in our calculation of close range coordinates, which we are going to do as a final exercise. Now, I think we have a few minutes left. Let me see. This equation has been manipulated in a way to show certain things. Let me just show the one that is important there. You can follow my derivation when you get the material. Follow my derivation. P naught is manipulated in a way so that that line segment, don't forget that our equation is P equal P naught plus a fraction T times P naught minus PA, or PA minus P naught, whatever it is. Now, that is the standard equation. Now, what PA minus P naught or P naught minus PA is a line segment. You can express that line segment in terms of direction and magnitude. Don't forget that if any vector has 2 properties mainly, it's more than 2, but 2, direction and magnitude. So we can express it as magnitude and direction. So to get the direction of this vector, P naught minus PA, which is a line segment, we are going to divide it by the magnitude. And that's what is done here. See the same line, P equal P naught plus T now times P naught minus PA is a line segment divided by the magnitude. It gives us a unit of direction vector. So we are expressing that equation not in terms of just the position vectors now. We now are expressing it in terms of the starting position and the magnitude and direction of the segment. Okay? And still a small proportion T will remain. And now what you see is that P naught can now be broken into magnitude and direction. P naught is P naught plus T over the magnitude times P naught minus PA over the magnitude. Now T becomes unspecified. It becomes unspecified now because we have already reduced it to direction vector. Okay, so you will see what happened. Now, going further in the derivation, if we represent this one as the direction of that line segment, we represent it as T bar. To take note of that, T bar. That is the whole of this one is T bar. Then we now change this T over P naught minus PA into S, another variable S, which is not defined. Okay, so we change it to variable S. Now, that simple substitution will give us an equation, another equation for the line. Any point P on that line be equal to the starting point plus a scale S times the direction. The scale S times the direction. You see that it is in the form of magnitude and direction. One thing we know here is that the direction has magnitude 1. Any direction vector has magnitude 1. So this S indicates the magnitude of this vector. So it means that if S is found, then any point along that line can be obtained as P naught plus that small proportion S now along that direction. Now, the beauty of the S is that where T goes from 0 to 1, S goes from 0 to infinity. What is infinity? What is infinity?
The limit of all numbers.
It means limit of all number. The number that is excessively large. Okay? So, but it can be as large as we want it to be. That means that S can be chosen to be as large as we want point P to be. That means that point P is no longer limited to between point P0 and the A, but it goes from point P0 to infinity. Use it to find coordinates of any point along the line, or from that point to infinity. Okay, that's the beauty of array. So the equation we have now has been broken down into array form, where array has direction vector whose magnitude is 1, and then there is a scalar which can be assigned to it as its magnitude. So any number can now be its magnitude, and you can find the coordinate of any point along that line. So it means that we have shifted the point A to go into infinity, so that we now know the limit of it that we want. We just specify S. So if S is 10 meters, you get the coordinate at that point. If S is going to be 100 meters, you get the coordinate at that point. If S is going to be 1 million kilometers, you get the coordinate at that point. So you have turned it to an array that it has only a beginning. Array has only a beginning, there's no end. The end is determined by the value S. Is that clear?
Yes, sir.
Okay, so we'll be using this equation now. Yeah. Yes. So we'll be using this equation now as our standard equation for a line. Okay, a line that originates at a point and can terminate at any point that we choose by specifying the value for S. Okay, so in this equation, once we know the starting point of the line and we know the value S, the direction T, if it's given, then we can locate the coordinate of any point along that line from 0 to infinity. That's simply what it means. It said, note that the vector equation given here has a starting point, T naught, and a direction vector, T bar. Two quick corollaries. Corollaries, I think, that you can derive from a condition or a situation. Number one, if a line is defined by two endpoints in a coordinate system, in other words, if 2 points are given, whose coordinates are known are given, it can be represented by the starting point and the direction. Okay? I hope you get that. If a line is defined by two endpoints in a coordinate system, it can be represented by the starting point and the direction. Number two corollary. Given the starting point and the direction of a line, it becomes a ray on which any point along that line, along the ray, can be located in terms of coordinates by specifying only the length along the line. Now, I want to share this with you. If you have ever used AutoCAD, right? If you have ever used AutoCAD for drawing anything, a box or any geometric object, it requires you to just specify a starting point and a direction, right? Once you specify, AutoCAD can generate 1 million points for you along the line. So this is the formula they use in all AutoCAD calculations. There are other software that compute coordinates and lines and things like that, do coordinate geometry. Sometimes they call it Kobo software. That's what they use. Okay, so they use lines and also curves too. So you need to take note of that. Giving an example, given that a line connects 2 points 090 to 3 minus 1, 1, number one, find the equation of the line in vector form. The equation of the line in vector form. Number two, find the ray equivalent of this line, right? Find the ray equivalent of this line. Number three, find the equation of a parallel line taken off from position 664. Number four, find the equation of a parallel line taken off 10 meters away from the starting point of this same line and in a direction given by 0, 20, 0. Now, that is solved for you on this page. Number one solution is in vector form. The single line equation becomes P equal A plus T B minus A. And that is given as this, just as simple as that, right? Just P equal PA plus T times PA minus P minus B and A, okay. The equation is P equal A plus T times B minus A. And that is P equal 090, which is A, and T into PB minus or B minus A. And that B minus A will give you this. Differentiate two vectors, just difference their corresponding values, and we put that here. And that is the vector equation of that line. To find the ray equivalent, turn the direction vector into a unit vector. And how do you do that? Just find the magnitude of the direction here, and then divide that magnitude into every element. That is what has been done here. And it's given as P equals 0.90, which is the starting point, plus 3 over 10.5 minus 10 over 10.5, and there's a mistake here, and then 1 over 10.5. Okay? Now, okay, the equation is being repeated, and all that. That's all you have. All the solutions are provided here. I'm going to get that. The perspective projector is the straight line from the object point passing through the projection center and forming a point on the plane or the image. So that is a line segment from the image to the object. And you can use this same equation for that projector. Don't forget, a projector is a line that originates from the object, passing through the lens of the camera and forming an image on the image plane. And that is a projector. It is a line segment between the projection center and the object point and the image point. Okay. Conceptually, two coincident rays are involved in perspective projection. Coincident. When two rays are coincident, means that they have the same direction. Okay. The position vector from the projection center to the image plane, okay, and the one from the projection center to the object. If you have a drawing fitting that, what's happening? Oh, okay. See that this lecture has a lot of unsolicited points. That's cut us off. Okay.
Hello, sir. When
Yes.
when should we be expecting the final slides so we know what we're reading for the exams?
I can't hear you.
So when should we be expecting the final slides so that we know what we're reading for the exams?
I would make that available today. I try my best. I have so many courses.
All right, thank you, sir.
But I will try today. Always cross-check with the class assistant, because the one that keeps custody of all the lecture material. You should be able to get it to him today. Is that clear?
Thank you, sir.
Is that clear?
Thank you, sir.
Now, I think we have seen enough of that example. I'm sure by the time we organize it, everything will be in place. Now, the last point I want to discuss today, before we close in a few minutes, is one that treats the image, the one that treats the image as a virtual 3D space. We have treated this before. The image plane is a plane space where you have length and breadth, the two-dimensional object. But we said that the image plane can be augmented in a virtual 3D space by adding the direction of the focal length as the third dimension. In that case, it is not a true 3D, but a virtual 3D space. Now, that is seen here. That is seen here, where, as you can see from this image, the coordinate of this is an image, and point coordinates for A and B on it are indicated as the coordinates or the pixel coordinates. Okay. Now, there are just two values, X and Y. But you can now augment it with the direction of the focal length and represent it in the extreme left drawing, where you have point A, for example, is represented now as a virtual vector, 3D vector, by adding a third dimension. Apart from the measured XA and YA, now have F added to it. F is the origin. And geometrically, this is the picture you have. This is where the camera is held, and then the image is formed on the focal plane of the camera, where you can measure the coordinates. And by adding those coordinates, which are X and Y, to F, which is the focal length, you have a virtual 3D system where a point does not just lie on the plane. It's a point that comes from the origin, the center of the length, to point here. And that's a virtual vector that has three values. Okay? And these three values are represented here as XA, YA, and F. So it means that a plane point measured will have a virtual 3D vector, which is represented as XA, YA, and F. Okay? That should be noted. So it's a virtual 3D space. Virtual 3D space. Now, we can generate that virtual 3D space on our own image by measuring the X and Y of points in pixel coordinates, and then centralizing. What we do is to measure the corners of the four images, which is X1, Y1, X2, Y2, X3, Y3, X4, Y4. Measure those then in pixels. Then we now compute a number by adding all the X and dividing by 4, and adding all the Y and dividing by 4. That now gives us the coordinate of the center of the image. And the center of the image in 3D form, we just add F to it. We add F to it. That is the virtual 3D of that point. Now, any other point that we measure, any other point that we measure x1, y, x and y. For example, we have x, c, and y, c. Then it can be computed by this formula that is given. It should have been xa. There's an error here. This should have been xc. Or maybe we'll put this one as xaya. Now, the correct xaya will be x measured, y measured minus x naught, y naught, which is the center of this image. And that gives us a way that we can turn our images we get with the camera in our phone. Use the image, the camera in your phone to take picture. When you load it on the computer, it's going to show you in pixel form. So those pixels, just measure the corners of it, the pixel, compute your x naught, y naught, and then that serves as the coordinate of the center. And the coordinate of any point that you now measure, remove the coordinate of the center from it, get the coordinate, objective coordinate of the point. And the point can now be represented as x, a, y, a, f. And that's the virtual 3D for the point. Okay. I'm not sure we have, well, we'll have to do this anyway, because you're going to get an assignment to use your camera to take pictures. That will be put in the lecture material that we'll get today. The lab assignment will be put there. Okay, but the bottom line is to get the virtual 3D coordinate system. Now, procedure for doing that is already given at the bottom. Now, this vector is used to represent the position of a point in a virtual form. What it means is that our image, even though it's a flat surface, we can treat it as a virtual 3D surface, for which you can now do magnitude and direction, and then continue our processing. Now, thus, the point A, X, and Y on the plane of the image be represented in Cartesian 3D space as A, X, Y, F, or in algebraic form, A equal X, Xi plus Yj plus Fk, where F is the focal length of the camera. Okay. Now, in other words, a point on the photograph whose image coordinate x, y have been measured and be represented as a position vector, a 3D space in which the third axis is the optical axis of the camera. That's what that message is telling you. And if a point is represented in 3D, I told you it can be represented either in the horizon system or in the direction angle system. And you get the same representation and the same result by using any. The advantage is that you can convert from one form to the other, which of course you can expect in the exam to happen. Now the virtual XYZ representation, which can also be represented in algebraic form, can now be represented in the horizon system, which is given as A equal magnitude A cos V cos H and all that, and then in horizon angle form as this. Okay, that's the message that place. Now, I want to skip this. This is for this is not for your class. This is for area photography, which you were supposed to learn in 517 or whatever it is. Now, pixel location are coordinates also. That's what this message is telling us. This is an image where you have the numbers inside those cells are the radian values or the digital numbers, or the location of the pixel in relation to this axis, the X and Y axis, are the coordinate of the pixel position. The first pixel here, which is a small square, has value 0, X is 0, Y is 0. Okay, X is 0, Y is 0, or column and row. The column is the X coordinate and the row is the Y coordinate. So the pixel at position, column is 0, row is 0, is value there is 0.1. What is the the coordinate, the pixel coordinate of the point whose value is 10 that I'm pointing at now. Who can tell me what the coordinate will be, the pixel coordinate?
So I think it's
We have treated this before.
3-2.
Huh? C2.
2-3. 2-3. Column row. 2-3.
Oh, 2-3, sorry, 2-3. Column.
We normally call it CR. CR. C for column, R for row. C comes first before R. So what is the location here? One that I'm circling with my cursor.
We said 2-3, sir.
Eh?
2-3. The column is the column 2-3. Yeah.
Okay, column 2, row 3.
Yes, sir.
Right? Column
Yes, sir.
2, row 3. But recognize also that 0, 0 are their own column and rows also. They have their value. So that's column 3. I mean, column 2, row 3. That's the value. What is the pixel on the upper right corner? What's the coordinate?
5-0, sir.
5-0. Beautiful. What of the lower right corner?
That's 5-6, sir.
5-6. What of the
Yes, sir.
lower left corner?
That's 0-6.
So you know how to. If you get your image inside the computer, that is what the computer will be giving you. Computer knows the location of each, and they going to give you. So when you get your image, put it and then read the pixel coordinate, then go back to this formula, this one that we have here, convert every point into XY centered coordinates for that something. Now, moving forward and getting to the end, we are representing that point, that position vector, which are coordinates on the image in terms of a Cartesian form. A is X, Y, F. And in algebraic form Cartesian, A equals Xi plus Yj plus Fk. In spherical form is A equals cos V sin H plus sin V J plus cos V cos H K in a right-handed coordinate system. Now, the other one, the last one in the directional angle form, the same vector, position vector can be written magnitude and direction, where the direction is indicated. Now, okay, that's a repetition. Therefore, the point PXY will be represented in any of the forms given, depending on what application we are doing. So for your exam, these three forms, there will be questions that you have to apply any of these three forms or convert from one to the other. So you need to learn the conversion formulas, where conversion formulas are also written for you in this form. So you can do your calculations and conversion from one form to another. But more essentially is to apply the equation of the line, or the equation of the line as a segment or as a ray to solving problem. That's what I'm going to dwell on. What I'm going to dwell on next in the next lecture, where that is next. Yes. The next lecture. Now you see this geometry. Finally, before we close for today, geometry of a single terrestrial photograph. You will see that this is the center of the lens. Okay, and the instrument is positioned on a station, a known point for close range. Actually, the name of the course that we are doing is terrestrial photogrammetry. Close range can be terrestrial or aerial. Aerial means suspended in air. Okay, so close range embraces both aerial and ground. What we are doing is terrestrial close range photogrammetry. Terrestrial close range photogrammetry. We will also do aerial close range photogrammetry at another time. Now, terrestrial photogrammetry, where you have your camera located on a tripod and that tripod is set on a survey station, just like you want to do your traversing. Now, this camera is beamed to see the rays coming from the object point. We see that this ray originates from the object point, goes through the center of the lens and forms an image. Okay, forms an image. Even though this image is on the back of the camera, we have transposed it to the front for convenience. So when the ray is coming, it does not stop here because of the positive image that we have. It goes to the lens before it comes to the image. But of course, you see from a point A, it is a single line that goes through the entire point to the lens. So that is a line segment. It is a line segment. It is a line segment, and we can consider that as a line originating from the camera position and going through to the image, positive image, and then going to the object. So it's a single straight line, and we can form an equation for that line to be able to compute. And the beauty of it is that from point O of the camera to point A of the image, small a of the image, we can compute that length if we measure the XY of this point A, XA, YA. And since we are doing a virtual 3D representation, the focal length, which will be given, is going to form the third axis. So that means we can form AX, Y, and F for that particular point. That F can be converted into direction for this segment. And since it's the same line, that direction is also true for the entire length. All we now need is the additional distance to go to that object. And we shall see how that is done in the next lecture. Okay, using that our equation. So you need to study the equation, both the magnitude of a vector and direction of a vector, and how they are plugged into that equation to be able to do computation. That we will do. I was thinking that we agreed to do another lecture this week. Would that be possible? Class governor?
Yes, sir. There's a lecture set for tomorrow, sir.
Let me hear you again.
I said there's another meeting set for tomorrow, sir.
Okay, we can do one tomorrow.
Can you hear me, sir?
I can't hear you well.
Yes, sir. Yes, sir. There's another lecture tomorrow. We
For
can do another lecture tomorrow,
for
sir.
5 to 8.
5 to 8. Yes, sir.
Yes, sir.
Yes, sir.
Okay. What time?
By 2, sir.
Okay, tomorrow.
Yes, sir.
That's okay by me.
Yes, sir.
That's okay by me. Okay, so tomorrow we'll continue. Before that time, you will have gotten this lecture material, yeah? So that you can follow me properly. Is that okay? Is that okay?
Yes, sir.
Okay, so we are starting from this point tomorrow. Hopefully
Tomorrow
we can finish. Tomorrow we can finish that lecture, and then we can begin to work some examples, and then you now do your lab and all that. So let's meet tomorrow 2 o'clock. The what? Someone is talking.
Yes, sir.
Someone is talking.
Yes, sir.
Are we okay with tomorrow?
Yes,
okay
sir.
With tomorrow? Eh? Is the class still there? Is the class still there?
Yes, sir. We are here, sir.
Is tomorrow lecture okay?
Thank you
Yes, sir.
very much, sir. Thank you very much, sir.
Okay. Bye-bye.
I said thank you very much, sir.
Okay, thank you. Thank you. Tosin,
Yes, sir. Yes, sir.
thank you for this lecture. They have agreed that tomorrow, 2 o'clock.
Okay, sir.
Huh?
Okay, sir. And then, sir, we have SVY 8 to 8.
8 to 8 tomorrow.
Yes, sir.
Tomorrow.